Okay, let's try another really involved problem. Fun times, okay? Fun times. So, what we're going to have two different engine inlets, okay? Yes, one simply has a shock wave. A normal shock right there. I have initial, this is the inlet, this is the exit. I have state 1 right here, I have state 2 right here. In the second one, I have a converging diverging nozzle. Something like this. Okay? This is the exit, this is the inlet. In both cases, I have a Mach number entering it that is 2.0, and I have an initial static pressure that is equal to half an atmosphere, and I have an initial temperature that is equal to 300 Kelvin. So same scenario for both of them. And my question then is, what is my exit Mach number, exit temperature, exit static pressure, and what is the ratio of my exit stagnation pressure to my initial stagnation pressure? And this last one right here, just so you know, that one is going to be a measure of the efficiency. If I was perfectly isentropic, then that value would be 1. And so the further I am below 1, the less efficient I am. So we want to see more or less what is this, how close is this to 1 for both scenarios. Okay, and we're going to assume, once again, as always, that gamma is equal to 1.4. I might not always do that to you, but at least for now, it'll make things easier for us. Nice. So we'll do the first one first, because it's going to be the easiest one. We have pretty much everything we need. Yeah, so let's just go to the normal shock tables. That's all we have to do. First one is just normal shock tables. That is it. So it's not going to be too bad here. So for M1 that is equal to 2.0, I'm not going to jump over the shock table since I showed that to you several times now, but you can see what I'm writing down. This will be helpful for future reference. For M1 that's equal to 2.0, I'm going to get that, let's see here, M2 is going to be equal to 0.577. I'm going to get that P2 over P1 is equal to 4.5. I'm going to get that, let's see here, T2 over T1 is equal to 1.688. And because I really don't want to have to go to Appendix A as well, I'm going to go back to my table, because I don't have this in my notes, and figure out P02 over P1 is, because that's going to save me some time. So I want this value right here, because then I don't have to find out what P01 is to begin with. I can actually solve this. I'm going to get both of these values. These will help me out a lot. Okay, so for a Mach number of 2, right here, P02 over P1 is 5.64. And then finally, the last one I'm going to get, I'm going to put over here because I'm running out of space, that P0 over 2 over P01 is equal to 0.7209. There we go. 0.7209. Now, with that, I have enough to solve for this first problem. Like, I already know the Mach number. I mean, that got the exit Mach number. We got that done. Happy days. Now let's get our exit temperature. So T exit is going to be equal to, let's see here. As a note, E and 2 are the same thing in this case. That'd be T2 over T1 times T1. It's going to be equal to 1.688 times 300 Kelvin, or 506 Kelvin. Okay, got my temperature. Let's find my exit static pressure. So PE is going to be equal to P2 over P1 times P1. My pressure one was, what was it? It was half an atmosphere, yes. So 0.5 times 4.5 is equal to 2.25 atmospheres. Okay. And then the final one there. Oh, I feel silly. I didn't need to find I'm not trying to find the exit static pressure. I just need the ratio. Well, it's already given to us. P naught 2 over P naught 1, which is the same thing, is equal to P naught exit over P naught 1, because how we define everything, is simply 0.7209. Now, that is not 1. Because it's not 1, it means it's not perfectly efficient because it's not isentropic, okay? So, now, let's do it for the second case. So in this case, I have an isentropic, and that should, I think, give you ideas of what's going to happen here. I have an isentropic diffuser, okay? Because we have to assume it's isentropic, otherwise we can't really solve the problem. If it's not isentropic, everything's going to go horribly, horribly wrong. Okay, so I'm going to redraw that. We're going to have to talk about some different assumptions we're making for it, and we'll go from there. Okay? Even if it's not okay, I'm okay with it, so we're just moving on. Seriously? Who cares what all of you think? Okay, so here is my isentropic converging diverging nozzle. Okay, first thing is I'm having to assume it's isentropic, because if it's not, I can't solve this problem, because I don't have any other ways and tools to use. Second thing is, here at the throat, I'm going to assume that the Mach number is equal to 1. And so I'm going to assume that that right there is a star, okay? Not really super important for a lot of things, but it does help if we know that. Okay, I think that's a good thing to assume, yeah. And did I give in the problem statement any sizes here? I did not, but I don't need those really, so that's okay. Making sure I'm not crazy there. Yep, okay. So with that, let's begin to solve for everything. So we need to find the exit versus the inlet properties. And here's the thing. If this is truly isentropic, I can already figure that out, okay? I can figure that out. And one thing it did tell us is that it has the same exit velocity for both, okay? We're assuming that they both have the same exit velocity. So I needed to know that, because if I don't have that, I can't solve. So I'm going to go ahead and say that m exit is equal to 0.577, because otherwise I can't really compare the performance. And so from that, we can solve everything else. Okay, so that looks pretty good there. I think we're good. So what we're going to have to do is we're going to have to go to Appendix A now. And we're going to find out all the stuff we need from that appendix, okay? Appendix A, because this is entirely isentropic. So we're going to go for a Mach number which is equal to 0.577. We're also going to go for a Mach number that's equal to 2. And we're going to find out the properties for A over A star, as well as T over T naught, and P over P naught. So let's go over there and find them out. Now, actually, to make things simpler for myself, I already have these in my notes. So rather than jumping around, I'm going to go ahead and give them to you. So this will be 1.217. This will be 1.688. This one right here will be 0.9376. This one will be 0.5556, 0.7980, and 0.1278. Okay. So we have all of our values. We want to know what is our exit pressure, what is our exit temperature, and what is P naught exit over P naught inlet. Now, the last one is the easiest one to tell you. It's 1. Because I assumed it was isentropic. I had to do that for that nozzle, otherwise I couldn't actually solve it. And since it's isentropic, remember we were doing that the P naught 2 over P naught 1, oops, No, that works still fine still. Is equal to some exponential, and there was a negative of delta S over R in that. We remember that from a little while ago. And so in this case, that right there is 0, which means that that ratio is 1. Okay, so that was the easy one. Now let's find out what our exit temperature is, okay? That will probably be the easiest thing. Yeah. Now, since it's isentropic, we know my static temperature stays the same the entire time. And so I can use that to help me out. So this is going to be equal to T exit over T naught, okay? And I also know what T naught over T inlet is, so that's T naught over T inlet times T inlet. So I have this one from the tables. I have this one just inverted from the tables. I know what that is. So I can plug all those in. So that means I have, let's see here, 0.9376 times 1 over 0.5556. And then I multiply that by T inlet, which is, let's see here. T inlet is going to be 250 Kelvin, was that right? No, it's 300 Kelvin. 300 Kelvin. And so that gives me a T exit of 506 Kelvin. The last thing we need to find out is what is P exit. And there's various ways I could do that. I can also realize that my stagnation pressure doesn't change. I'm going to do that one because it makes it easier on me. We're going to use the same little forms we've been using. I could also use my isentropic property relations, like the ones you learned in thermo you can still use here because it was completely isentropic. So let's do it the other way though. So P exit is going to be equal to PE over P naught times P naught over P inlet times P inlet. So just like I did it for the temperature. So I get 0.7980 times 1 over 0.1278 times, I believe the pressure was half an atmosphere. Yes, it was, 0.5. And that gives me a pressure of 3.12 atmospheres. Happy days. Okay, looks good. Now let's compare. So for the same exit velocity, what is happening here? So first off, what I can see is that the exit temperature is actually identical, 506 Kelvin in both cases. The reason for that is because my stagnation temperature was constant the first time as well, so it works out fine there. But my pressure is much higher. I have 3.12 atmospheres here, while before I had 2.25 atmospheres. My exit pressure is much higher, which is going to be beneficial to me. And then finally, I'm not wasting anything. There's no entropy losses, so my stagnation pressure is constant the entire time. So that converging diverging nozzle is much better than having just a normal shock do the compression for me. And there we go. There we have it.